Obviously, my friend Charlie Roberts, I've been sending emails to the users list that I assume you guys read, which is why you're here, so I won't reiterate everything, but I met Charlie right when I started at UCSB. On like the very first day that I got there, I was like, oh yeah, this is obviously a student I'm going to be working with. He was doing a lot of awesome stuff with open sound control. And when I first started at UCSB, you were like the one student that I was like, yeah, I can definitely relate to that guy. And indeed, we did relate, and we worked together very productively for basically almost my entire time at UCSB. You were like a second year PhD student when I started.
A year before you, and we left at the same time.
Yeah, we left pretty much exactly at the same time. So he was their authors. I was on his master's thesis. We worked together in the Alisphere. We did a lot of technical stuff together and designed various software. And I would like to take some tiny bit of credit for Gibber as a sort of research mentor.
Sure.
Charlie definitely did all of the coding work. I still can't really write a JavaScript program that works perfectly the first time. But I've been harassing him about various things throughout the existence of Jibber, for better and for worse. Charlie is now a first-year assistant professor at, like it says here, School of Interactive Games and Media, Rochester Institute of Technology. So there's a whole other discussion that I guess Julius was starting to get into about what's that all about. It's like a sort of video game program, which is not going to be the focus of your talk today, which will be about making source code dance, visualizing algorithms in live coding performance. So I'll let Charlie say the rest. So let's welcome him. Thank you very much for being here.
Thanks to Matt and to Karma for having me here. So yeah, I'm from RIT in a place that's a little bit colder than it is right here, right now. But it's been a really great place. I'm in the School of Interactive Games and Media. It's a 800 student program. It's in the top 5 of the game design programs in the country, which apparently there are over 400 game design and developments just in the United States alone. So lots of really, really bright students in there and lots of really, really interesting research being done as well. So it says interactive games and media. I am more on the media end of the equation, although I wind up teaching both game students and media students, and sometimes game students who are doing things with audio, which has been really rewarding and interesting. But today I'm going to be talking about live coding performance, and as Matt was talking about, the environment I created called Jibber, and my work and research on using visualization techniques to improve both performer understanding of what is happening during a live coding performance, and also potentially improve audience understanding of what's going on in a live coding performance. So I thought I would start off by discussing what is live coding. I know this is a topic that's at least somewhat familiar to many people in the audience. But here's a list. This is the International Conference of Live Coding website. The first international conference happened last year. The second one will be happening in October in Hamilton, Canada. And when everybody registered, they were asked to provide their definition of what live coding is. And you get this giant list of things, some of which are humorous, some of which are a little bit more interesting, but the main thing is there's no one clear golden standard definition of what live coding is. And a colleague of mine, Graham Wakefield, and I actually just finished up a book chapter that really delves into the issue of what exactly live coding is. And we really just came up with very generic definitions and tried to provide an overview of all the different types of practice that are out there. So our very generic definition is this. In live coding performers create time-based works by programming them while these same works are being executed. And so this is specifically designed to be as open-ended as possible. The minimum thing is you are authoring works as they are being exhibited. That's kind of the minimum criteria that we established for that. One thing that we left out of this is the criteria that you have to actually project your source code. If you're familiar with live coding performance, that's often a really central part of live coding performance, but it's not a part of everybody's live coding practice. And there's actually a lot of debate in the live coding community about what it even means to project source code while you're performing. What does it mean for the performer? What does it mean for the audience? Does it really serve any benefit? Does it just detract? Some people say that if you're doing they have these events called algoraves, where live coding performers perform one after another in a kind of like a DJ style set, and supposedly people dance. Sometimes, once it gets late enough in the evening, enough drinks have been had, people definitely do dance. Yeah, there's the idea that having a bunch of code up on the wall takes away from the mood of a dance club atmosphere, and maybe it's not the best thing to actually be doing during these performances. So yeah, there's some interesting questions about that inside of there. So I thought I'd start with a little bit of discussion of some historical precedents of live coding. And this first one, did I write down the time to zoom to? Yes, 3:30. This is Tom DeFente's Tom DeFente's GRASS program for doing vector graphics. This is back in 1976, and we're going to see him do some live coding.
But first, you can see the room
and with some video processing, we're actually seeing him project the code as we'll see in a second.
Still off. What we've done here is put up some infrared lights, and Cross-Eye over there has an infrared sensitive camera, so we can show you the working environment of the room while we're actually doing things and still get high quality video without the room lights. And the regular TV cameras are not sensitive to infrared light. First thing we have to do to show you how we make this little flying starch molecule is restart the system. We're also superimposing the BTO5 type on the screen.
BTO5.
We get the starch molecule up.
So yeah, the code, this is the output that you're seeing right there, and then you're actually seeing, of course, his type.
The first thing anyone does with propellers is rotate them. But that appears to be the wrong axis.
And this is also being post-processed by Tom's partner in crime, Ben Sandine,
right away.
Who's doing all the video processing, post-processing
of the starch molecule
with custom analog hardware that he designed, the Sandine image processor.
That's easily done.
So one of the things that really interested me about that particular video, spacebar again, is that he had this system for really easily assigning the physical controls that he had sitting there on the table to any particular parameter inside of his running program. And in fact, it's a type of reactive programming that he had implemented back in the 1970s that allowed him to say, oh, take this knob, take this button, take whatever type of signal, and just feed it into this particular signal for the graphics properties, and all the transformations required take place, which is something that happens in Gibber as well, that'll play into some of the visualizations that I'm talking about. So that's one early example. In the audio realm, one of the first ones that's often talked about is Ron Quivila's 1985 performance at STIME. He was programming in fourth, and the performance ended with a crash, which led to this quote from Curtis Rhodes in his review of the performance in the Computer Music Journal. The reality is that personalized homegrown hardware and software for all the freedom of expression they can afford are especially subject to flakiness. And I wish I could disagree with that statement, but I would say more of my performances have ended with crashes than not at this point in my live coding career. Hopefully that's something I can even out as I go along. There are also early performance...
50-50 is your
50,
target?
Yeah, target. You want to have risk, you want to have danger inside of there. You don't want it to be safe. There was one performance I gave at MIT actually where I crashed the performance, but then I copied all my code, restarted Jibber, pasted it in, and got it running again. And I had multiple people come up and comment that that was their favorite part of the performance, just seeing that it was possible for me to crash, and then the excitement of whether or not I'd actually be able to get it all running again, which led me to think maybe I should start deliberately crashing in the performances. I haven't done that yet, but it's been in the back of my head.
It's like sawing through your strings if you're a violinist or whatever, sawing halfway through.
Yeah, exactly.
Yeah.
There's also early performances by the Hub, a networked musical electroacoustic ensemble where people could walk around to see the various computers and look at the screens and see what was happening. And there's a kind of an early precursor to projecting source code. But the more canonical live coding performances where you have this idea of a person sitting up, creating software in real time and projecting all the source code of the software that they're creating started more about the year 2000 with Slub Premiere Performance using a set of software called Feedback.Perl by Alex McLean. And then in 2001, you have Julian Ruber, who performs in New York using his JitLib extension for Super Collider. And the advent of Super Collider and also this JitLib extension really led to kind of an explosion in the live coding community. We have Guz's contribution with Chuck, Andrew Sorensen, Andrew Brown using Impromptu, a scheme-based live coding environment. Dave Griffiths and Gabor Pap create Fluxus, which is a racket, racket is a Lisp, or is it a scheme? Can it be a scheme? A dialect of scheme?
Scheme is a dialect of
Lisp. Scheme is a dialect of Lisp. I want to say racket is a dialect of scheme. I don't know if that's appropriate. But it's definitely a Lisp. Lots of different languages. Lua AV created using Lua. Thor Magnusen creates Ixielang based on top of Super Collider. Overtone, a closure-based environment, also based on top of Super Collider. Some web environments, my Gibber, Live Code Lab, 2 different web environments for live coding. Sonic Pi. There's been a ton of environments that have been created over the last 15 years, and this is really just a small fraction. Matt, did you find the answer?
Racket is a full spectrum programming language. It goes beyond Lisp and Scheme with dialects that support blah, 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 blah.
Subject for further investigation, apparently. So there's a real...
dialect.
Yeah.
Oh, nice. So there's a real diversity of practices out there in terms of the tools and the languages that have sprung up over the last 15 years, which is really exciting. It's really interesting to see people create these new sets of software. And even here today, I've seen potential new software that might be used towards this performance practice that it's pretty exciting. So one of the core aspects that we've mentioned that not everybody does, but I tend to think of it as being important is this idea of projecting the source code. And this means lots of different things to lots of different people. There's the idea that you're making the process, the methods of production transparent. So you know that the person isn't just up there checking their email and playing a CD while they're performing. You can actually see action and activity taking place. There's the idea that by showing people the tools that are actually being used, that people might feel empowered to try it themselves, and that you might make programming less intimidated for some of the people in the audience. And some live coding environments, like Sonic Pi, and I like to think also like Jibber, are kind of lean more towards that side of the spectrum. Ixielang as well, trying to make things simple to do, whereas other libraries or environments are kind of designed to be more virtuoso setups. I don't know if the authors themselves would necessarily say that, but the authors are definitely virtuosos themselves. I'm thinking of Impromptu and Extempore in particular by Andrew Sorensen. These are really powerful libraries that have a little bit more of a learning curve associated with them. So with that in mind, if we're thinking about the different ways that these tools can be used and thinking about how the audience perceives it, for me it becomes interesting to think about how we can try and improve the audience understanding of source code in addition to the performer's understanding of code as it appears. And this is a topic that's seen a lot of research, not necessarily resurgence, but a lot of interest lately, particularly following, there was a very influential essay a few years ago by Brett Victor called Learnable Programming. If you haven't read it, I highly encourage you to read it. It's an online essay with tons of interactive examples, really thought-provoking. And this prompted what we're looking at right here, which is the Swift playground inside of Xcode. And in the Swift environment, we're looking at Swift code here on the left. We have an intermediate stage right here, which is showing us what the output of individual lines of codes are. In this case, when I create a string that says hello playground, that's what the output, the result of that particular string is. This is showing how many times particular lines of code have been run when a for loop is executed. And then over here, we're seeing the actual results of all of that happening. So ways to kind of think of programming more interactively than just write everything, compile, see the results, rinse, repeat. So this is the light table environment, which is a web-based programming, or uses web technologies behind the scenes. And here we can see the output over here on the right, but inside the code editor itself, we have this little modal window that's showing the state of this particular mesh object. So all of the different properties that are associated with that mesh object and all the different values that are currently assigned to that particular property. And you can monitor these properties live in real time and see how they change as a program actually runs. So these ideas are really appealing in live coding. You know, the idea that you can have source code and be creating music, be creating visual art, be creating choreography, creating whatever it is that you're live coding, but then also show how the algorithm is proceeding underneath this, behind the scenes, what's actually happening and what the current state is and how that state is being modified. And so a few people have done experiments with this in the live coding community. One example of this is Irmis, which is a Lua-based live coding environment. And so they kind of take a similar approach to the Swift editor. They have this idea of a live variable view, which is a separate area to the left of the editor that displays the current state of different variables. And you can basically specify any particular variable or object to be dynamically monitored. It'll show you the values associated with those variables inside of this window right here. This is visualizations inside of Impromptu and Extempore. Impromptu is a scheme-based system that I mentioned earlier by Andrew Sorensen. And here he's using extra widgets that are kind of added on top of the heads-up display style widgets that are placed on top of the source code editor to kind of show, in this case, the progress of sequence and the progress. These are like piano roll style editors that we're looking at up here at the top. And unfortunately, this particular set of widgets no longer, at some point it broke a couple of years back, and they haven't, the widgets and the extensions were created by Ben Swift with Andrew Sorensen, and they haven't ever got them up and running again. So I've actually never seen these running in person. They look amazing from the paper though. Hopefully one day they'll get around to getting them going again.
Like how that wedge kind of looks like a Lisp single quote character.
Yeah. One of the first live coding performances I actually saw was Thor Magnusen performing with Ixi at ICMC in 2011. And this was what really got me interested in this idea here. And so I'm going to show a little bit of this. So Ixi is a domain-specific language that's layered on top of SuperCollider to enable really quick sequencing. And you'll see here as he creates these patterns, let's start it right here. So he's got these two piano patterns he's created that are playing the notes from piano phase. And they're starting out playing perfectly in sync with one another. But watch what happens when he tells them to begin playing out of phase. So the idea that you could have your source code and actually have it be dynamically modified by the running program underneath of it and still be able to edit and interact with it in all these different ways was super exciting for me when I first saw him do this performance, and really inspiring. And he has some other visual annotations that he's added to this as well. In another environment created by Dave Griffiths, this environment is called scheme bricks, and the bricks basically denote control flow inside of here as they move between the different objects. And you'll see flashing that's occurring. So every time those flashes happen, that's showing that a message has reached that particular object. So it's a visual indicator that some type of control message signal has reached that particular object, and some type of node event or other type of event is then occurring at that particular location. So an easy way to kind of show what objects are doing it and when they're doing it in this visual programming language. It was funny when I got this video and I was watching it. I've never seen a scheme brick performance. I've just seen pictures of it, but I never realized that the environment itself was 3D until I watched this little part of the video clip right here. I kind of want to see him start spinning it around and. So this brings me to talking a little bit about Gibber. So I'll give a little introduction to Gibber, and then show some of the different types of visualizations that work inside of Gibber, and talk about some of the responses to that I've seen so far. So you can get to Gibber by just going to gibber.mat.ucsb.edu, or gibber.cc works as well. So it's a browser-based tool for doing live coding. It works in modern web browsers. And it's all JavaScript, from the end user programming language all the way down to the audio engine that powers it underneath the hood. So I'll just give some examples of quick Gibber code. So this is kind of like the hello audio world example for Gibber. Make a drum beat where X's are the kick drums, O's are the snares, asterisks are hi-hats, and minus is a open hi-hat. And you can really easily set up multiple beats going at once with kind of different type of polyrhythms. Change properties of that. So there's a little bit of the audio. There's of course other types of synthesizers for doing chords and bass lines and leads and whatever else. Lots of different effects. There's also a visual engine inside of there. So I can say, let's make a cube. Let's spin that cube 0.5 radians per second. Let's make the scale of that cube a little bit bigger. And then I can also do things like, let's take our drum beat that I had earlier, and let's say I want the scale of my cube to track the drum beat. So I can just use a simple assignment to map that to the output. And this might be the most DSP part of this seminar. So behind the scenes, there's a lot of metadata that gives the minimum and maximum values for both the output property here and the scale property right there. It also gives the time scale that the two different properties operate at. So it knows that one's operating at the graphics frame rate and one's operating at audio rate. And then it does the appropriate transforms to kind of map one property to the other. And you can do all sorts of different manipulations of those mappings after the fact as well. Inverting the mappings, you can sequence the inversions, you can sequence changing the ranges of where the mappings actually occur to. And that also allows you to do really simple things like make a sine wave and map it to. So right now, maybe that's going the wrong way, so I can invert that. So you can kind of mix and match audio signals, control signals, and these graphical properties without having to think about all that stuff that happens behind the scenes. And that'll come into play when I talk about some of the visualization stuff inside of Gibber as well. There's also a database backend for Jibber. So if I go here to browse, there's a bunch of different demos that appear. So here's a little mouse trail demo. So there's 2D drawing in addition to the 3D stuff inside of it. There's some nice little shaders to play with. So let's make a kaleidoscope shader. And now I get really different things when I wiggle my mouse around. Lots of different shaders. Here's an example that's creating some music and then visualizing it with an FFT. So let's say these top 8 or 9 lines are creating all the music right here, the bass line, the drums, and modulating the scale being used. A couple of lines to set up the FFT, and then 9 or 10 lines to actually draw the results. So a lot of what I think about in Jibber is thinking about, well, how can I think of things that you might want to do when you're just getting started programming that might be exciting, and how can I distill that down into really easy to use API and user API, like those reactive properties that we were just looking at a second ago. And when you create your own, we call sketches in Jibber giblets. When you create giblets, you can publish those to the database. The database is searchable. You can tag things, look at the works of other people, and everything's versioned. So you can see the previous revisions of your files and go back and forth between any of them and look at them. All right, is that what? Oh, I will say one other thing again, because it's the DSP seminar. So Jibber does things very differently from most web audio systems. The web audio API that's included in the browser does buffer-based processing. When I got started creating Jibber, I was really interested in per sample processing. At the same time I was interested in per sample processing, the only way to have audio that worked cross-platform between Firefox and Chrome was to use this thing called the script processor node, which basically lets you do all of your signal processing, all of your sample loops inside of JavaScript. So I created a library called Gibberish that kind of optimizes this. And the way it basically works is you break your demo. Okay, that looks a little better. Okay. So on the right-hand side over here, I have this code. I'm blocking it with my head. This is the object-oriented code that a user would write. It's much more lower level than what we saw in Jibber, but kind of making a couple of sine waves, using those sine waves to create vibrato. And then it takes this and creates an audio graph behind the scenes, and it flattens that graph into a list of function calls where it inlines the as many of the arguments as it can into the actual audio callback. And then this is basically the body of a JavaScript function that is created that is then called 44,100 times per second. So because this is per sampling, that lets you do things like chaotic oscillators, feedback networks, physical modeling that you can't do with the built-in nodes that come with the web audio API. Unfortunately, there's a lot of other trade-offs that are not so nice about using these per samples techniques. There's the standard performance penalty that you accept with it, but there's also a latency hit that comes with it in the current state of the web audio API. They're working at Google right now. In fact, a Stanford alumni, is currently working on creating a system that allows you to run JavaScript-based sample-level processing within its own thread with lower latency than what's currently present. So some of these problems should actually go away, and there should be a more full-fledged solution for doing per sample processing in the browser soon. All right, so let's look at how some of the visualization stuff works inside of Jibber now that I've gone through all of that. Most of the visualization stuff revolves around the idea of patterns and sequences in Gibber. So whenever I have any synthesizer or any instrument that I've created in Gibber, I can sequence a method by, well, okay, first of all, if I want to play a note, that's the method right there. I'm creating an instance and then I'm just calling the note method immediately. 0 refers to a default global scale, the first note in that default global scale. You can also use frequency values or note names if you want. But let's just stick with 0 right now. Now for any method or property in Gibber, I can sequence that by just adding a call to .seek at the end of it. .seek accepts 2 parameters, a list of output values and a list of timing durations. You can't call the method and then call .seek, so just refer to the method and then, yeah. So now it's looping through these numbers, alternating between a quarter note and an eighth note right there. Behind the scenes, these lists of numbers that I give it are being converted into pattern objects inside of Gibber. Patterns are just functions that when you call them, immediately return a value. So if I say pattern 1, 2, 3, 4, and I can just flash the results right here of calling that function that gets created. I get 1, 2, 3, 4, and it just loops. This is the default behavior. And then those patterns can have all sorts of transformations and filters applied to them to change their behavior. So you can set up patterns to repeat certain notes, you can set up patterns to skip certain notes or limit the range of the values that are actually being outputted when the function is being called. There's all sorts of transformations that are possible. So after I run this note.seek method, I get a pattern of values and a pattern of durations that actually get created. And this is what the kind of the parsing stage for these visualizations I'm going to be showing is handling. So this is giving a rough overview of what happens. Whenever I execute a code block in Gibber that creates an object, I get a pointer to the entire code block. When I say the block of source code in the text editor is what I'm referring to, I get a pointer to each of the arrays associated with the 2 patterns that are created, and then I get pointers to each of the values that are present inside of the arrays. So I know the positions in the text editor of all those different things at any moment in time. And once I've done that, now I can start highlighting those values as they're being played. So this is the kind of the first indicator that I worked on, kind of drawing a little bit from that Fluxus example, flashing to indicate activity, but then also showing what value is currently the one being processed, so you can get an idea for what that actually is. So it makes a little more sense as you're going through the pattern what's actually happening there. And if you have something like a drum pattern, you can immediately kind of see, oh, the X's are the kick drums, the O's are the snare drums, and start to infer more about what's actually happening in the pattern than you would have been able to before when I didn't have those annotations turned on inside of there. So I tried a few different ways to kind of use these visualizations. This is kind of the last one that we settled on, but in consultation with Matt, we had a few different ones that we tried. I never changed this, so I have to look up the code for what this is. Phase indicator styles equals underscore. Okay, so here's one where it's just putting like a small underscore underneath of that. I had one where you just had a flash. Didn't clear the underscore. Naughty Charlie.
Why did it stop for the drums?
You haven't really
And
explained the evaluation model, but he stopped
Yeah, right.
all evaluation and then he like re-executed that one line, but not the other line.
Okay, so it isn't actually all the time evaluate everything.
sorry, yeah, that's a good point. So in Jibber, you highlight a particular block of code and hit Control Enter to execute it.
Okay.
Yeah, so it's not constantly rereading everything. So flash underscore, we saw the border flash. One nice thing about the border flash is if I do something repeatedly, it'll give you this kind of, not if I leave it like this. Dang it. Flash border. Of course. So it kind of gives you this circular motion, so you get the sense that it's happened repeatedly. Because if it just stayed the border there, and even here you get at least a modulo 4 representation of how many times it's repeated, which may not be perfect, but it's something. It's better than just having it continuously flash. And also at really high speeds, the continuously flashing can actually be pretty annoying if that was the bright white flashing, for example. So having it move around was kind of a compromise for that. Another thing that we've got inside of here is displaying how functions, what the output of functions are over time. So when I create a sequence, instead of putting a list of values right here, I can also put a function directly into sequence commands. And that just means that for every time the sequence is triggered, it'll call that function to determine either the value that's outputted or the next timing value that it wants to use. So one that I commonly use is just rand_i. Rand_i is a function that returns a function that generates a random number between two values. So if I run this, so what I'm doing now is I've inserted a comment, so it's showing you what the current value is that's present there. Otherwise, what is being generated right here would be completely opaque, of course, except for the audio result. But this is giving you some type of insight to what's actually present there. And the other method that I experimented with was to do replace. So in this example, it's actually replacing where the function was right there with what the current value is as it's being outputted. And if I clear Jibber, it returns to what the original source code was, so you don't lose that after the performance inside of there. And one other,
Can you clear individual code blocks, or
you
do you
can
have to-
stop the sequences.
Okay.
Yeah. Oh yes, you can. Sorry.
Yeah.
Yeah. If I just do a.clear, that clears it, or there's a shorthand which is just a._, which is really not that much shorter than a.clear, but that's what I use during performances. And the last one I want to talk about was one that was kind of a little bit more fun. Using this kind of reactive mappings that we looked at earlier, I was thinking about how we could use other properties of the actual text to display information about what's happening. So let's take this drums that we're creating, and now I'm going to say I want to take the blur property of my text object and assign it equal to whatever the current output value is. So create a mapping between these two elements. So now it's blurring the values based on that. We can also do b.text.letter spacing equals b.out. All sorts of really, really goofy things that you can play around with by doing this. I was pretty excited when I first got this to work, and I think I've used it twice in performances, and never really gone back to it. Yeah, and also some results of a survey I did that kind of talk about that in a little more detail. It hasn't proven to be a very useful feature by any means, although I keep trying to think of ways that it could be useful. One thing I thought that might be kind of neat actually is if, not exactly this, but let's say you do a fade on the master volume of your performance, if like the text all faded at the same time in opacity, or like maybe there's more opportunity for metaphor using the text than what I've experimented with by blurring in that quick example right there. So I did a little survey about this, kind of showing people different ideas. I was curious to see what they would think about it. 102 respondents from the Gibber mailing list, the live coding mailing list, various UCSB mailing lists. It also got forwarded to some kind of hardcore CS mailing lists. I got some really interesting responses from people that I assume were from those lists. I should have put one of those in there. Yeah, one person that said, I pretty much hate every thing that you're doing in this entire survey. That was useful feedback. But he did, yeah. So all this stuff, programming experience, a lot of people had seen a live coding performance before, and a lot of people had done live coding performances. Many had used Jibber. So some things that I thought were kind of interesting, a lot of people preferred the border phase indicators versus the flash. What was most interesting to me about this is when I went around and asked people individually, like my friends and other people in MAT, the opinions were super polarized about this. Like the people that preferred the flash just could not understand why anybody would prefer the border. The people that prefer the border representations couldn't understand why anyone would want something so obnoxious as the brightly flashing background. So I thought that was kind of interesting. Most people preferred the use of code comments to indicate the function output compared to replacing the function in the source code with its output. People preferred muted colors for these types of annotations. And almost everybody, except for probably that one guy that I mentioned, or girl, I don't know, one guy or lady that believed that other live coding environments could generally benefit from this line of research. And then in regards to those text things, 2 subjects back to back. The first subject, size change and blurring look like gimmicks rather than useful HCI features. The next one, the blur effect looks dope. So yeah, I'm leaving it in there if people want to make their drum beats look blurry. That's something I can provide to them. So as I go towards my future work, one thing I want to look at, this survey was a good step to kind of get some ideas about how people think about, one iteration of these annotations versus another. But I'm more interested in trying to maybe quantify in some way how this might affect audiences. So I've been looking, designing experiments with Amazon Mechanical Turk, trying to get large numbers of respondents to look at a version with the annotations in place, a version with no annotations, and then also the control, which is a version that has incorrect annotations in place, with the idea that some people might just be really excited about seeing things blink and like things more, even if they don't make any correlation between what the blinking is doing and what's actually happening in the music. So trying to get some idea of what the impact of this could be on a generic audience as opposed to the survey, which was 75% of the people had used some type of live coding environment in their life. And I know I'm running short on time, but I wanted to close with a example performance, and then maybe hopefully I'll have time for some questions as well, and people that need to leave and go downstairs, please feel free at any point. I like to start with these first couple of lines when I do this, when I talk about this, because it shows off some of the stuff we've already talked about. Gratuitous text player there at the end.
Not even in his free time.
Obviously, there was a bug that happened there. I have no idea. Something around this line. I don't know what happened, but things got crazy. Yeah. Any questions or?
How do you synchronize? So when you start another line, how do you get it synchronized with everything else?
Yeah, so the control enter executes code immediately. Control shift enter waits until the first sample of the next measure.
Mm-hmm.
So if you execute everything while holding down the shift, in fact, sometimes I think I should switch them because if you're doing any type of thing rhythmic, you wind up using shift all the time. That ensures everything lines up.
Mm-hmm.
Do you have to be online?
You can set up a server to run it locally. I have instructions for that in the GitHub repo that kind of walks you through it. I also, at one point, I had an Atom plugin that lets you do it, but that broke and I haven't fixed it since then. But yeah, hopefully I'll get back. I should have mentioned another thing. In addition to the future work with the Mechanical Turk, I'm actually working right now with Graham Wakefield on a plugin that runs in Max for Live that lets you use kind of the JavaScript and Jibber syntax to control the Ableton, synths and audio units or VSTs or whatever. So basically just outputs MIDI data that then gets forwarded to the instruments, and we'll also have the visualizations that I've been showing inside of it.
So is there like a global time signature that?
Yeah, and you can change that and sequence changes to the time signature, and figuring out how things like that interact with Ableton is some interesting things I haven't quite wrapped my head around yet. But yeah.
How much load does it? I mean, what's the CPU load when you run lots of stuff in the browser? Because there were glitches.
Yeah, of course.
Where are they from?
So the problem, so one of the other problems with doing this per sample processing that I was talking about currently, which again should be fixed soon, is that it's all single threaded. So the code editor, the visualizations being added to the code editor, you scrolling, and the audio callbacks all happening in the same thread. So that's where those glitches come from.
Have you thought about using the Web Audio toolkit? They have a lot of stuff they're developing.
Yeah. So when they get this other system called Audio Workers finished, then the JavaScript signal processing, the per sample processing, will be able to run its own thread, and that'll take care of all of these problems, I hope. Really looking forward to that. It's going to cause so many other problems that I'll have to deal with. I mean, there is a lot of beauty to working in one thread.
It's going to be synchronized.
Yeah. There's a lot of really nice things about it. So, but I'm actually already having to do some of that work to kind of disentangle the visualizations from the audio in terms of the threading with the stuff I've been doing to make it run in Max for Live. So I've got a head start on it.
Does your environment or any of the others you've studied have any way to record the keystrokes that are entered so that they can be played back, beyond just say screen recording or videoing it, because there's a performative element to that too.
For sure.
You might have something that was really, really cool and you can't just show a video of it and you may not be able to do it again easily.
There's a super collider quirk that lets you do that. I can't remember what the name of it is off the top of my head. There's a researcher at University of Michigan, Sang-Wan Lee, who created a JavaScript system for doing those types of recordings in the context of web-based live coding environments. And we've talked about getting it into Gibber and never quite managed to sit down for a couple of days. I have a trip out to Michigan in a few months, so maybe we'll find some time then. But yeah, I think that's a great idea. I mean, right now I have this way of publishing where you take the entire source code and you put it online, and then you could send your friends links and they can go and run the source code. but it would be a lot cooler to just send it as an editable performance that you could interact with as it was happening inside of there.
There's also the chat system. Just in terms of like telling your friends that you sent them source code, you could.
Yeah.
We have used that for performances too.
Yeah, we've done some network. I didn't even talk about that, but there is also some affordances inside of Gibber for doing ensemble practices. There's a shared clock that you can use for synchronization and the ability to see the code that other people are writing and manipulate that code as well as your own code.
What kind of shared clock? How does it work?
It works via that robots thing.
PID.
Yeah, it works via a PID control system. So it's constantly kind of undershooting and overshooting and gradually stuff. It's actually coming from Santa Barbara to wherever you are. And I don't know, it amazes me that it works at all. But it works okay. I've had people, I've tested it over in the UK using it. People at Louisiana State have taught summer camps where they've had many groups of kids at the same time all doing performances using the tools. It breaks down when you have an extremely large number of users in the same group, but I actually think that's not due to the clock. I think it's due to the code sharing part of things that's happening. I think if you try and have too many shared editors at the same time, it breaks. So that's something I just need to fix.
So as long as you are in a network which has the same distance to the where it comes from the master clock?
It tries to take all that into account.
Oh really?
Yeah. So there's
vector clocks.
There's
synchronization.
There's two modes. There's a physically co-located mode, and then there's a physically
Remote.
Thank you. Mode that you can do the performances. So in the co-located mode, it's trying to make sure that everything's like sample locked together. When the remote mode, it's not worrying about that as much.
This code is in there too?
This code is in there. I think it's broken currently. So write me an email if you try and use it and it doesn't work. There's a paper that we published on this in the proceedings of the live coding conference last year. It describes the technique. The technique was taken from a Roger Dannenberg paper in the late 90s, I believe. And that's cited in the paper, of course. Well, thank you very much again for having me.